imagine that you received the results of your performance for the last year, and you were shocked because you didn't see it very well, or you didn't see it as expected as you would think it will be. So you decided to write a plan that measures the progress percentage of your achievements relative or at each month. So you will start record the percentage of your progress for the first month, second, third, fourth, until the whole year. And we know, once again, from this table, that 1 year is equal to 12 months. So if you want to write your plan or your progress of this plan for a whole year, you would write, or you would collect the first 12 months, and you'll see the performance of your progress with each one of them. So we will start saying 1, 2 for the first month, second month, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th. Okay, and you'll see, suppose that, for example, your progress is something like 12% for the first month of the new year, 20, 28, 36, 44, 52, 60, 68, 76, 84, and then for the 11th month, 92, and then for the 12th, the last one of the year, 100. Now, you want to see the relationship between your month and the progress percentage. You want to understand what you did in this new year, so that then in the future, in the next years, you can develop yourself and achieve more percentages than these percentages for each month. For example, if you understand the relationship between this month and this progress in this year, maybe for the next year, because you learned from your mistakes, you will see that for 1 month you will achieve, for example, 30% instead of 12%. So you need to understand the data. One way to understand the data is by plotting the data. Why? Because if you plot the data, if you draw or if you graph the data, just terms we use in engineering, you then will know what will be the equation that explains this kind of behavior. Like, for example, if I put 1 month, this equation will produce 12%. If I put 2, then this equation will produce 20. I want to find this equation. So it seems that I am putting values of months to produce values of the progress percentage. The values I'm putting in the equation are called independent variables. Independent variables, which in this case will be the months. And the values that are shown after substituting the independent variables in a certain equation are called the dependent variables, which means in this case it will be the progress percentage. It wouldn't be clear now. If you are new to this, it wouldn't be clear, so I don't blame you. But I want to show you a real example with a graph and with an equation, and we will understand it step by step, of course in an Excel sheet. This is what your graph would look like. If you draw the months, the independent variable, with respect to the progress percentage, the dependent variable, you will have somewhat a constantly going upward line. Now, whenever you have a constantly going upward line or constantly going downward line, then it means that the relationship between the months and the progress, or X and Y, is linear relationship. Look at this 12, 20, 28, 36. Always the difference is 8. From 12 to 20 is 8. From 20 to 28 is 8. All the way to 100. 100 minus 92 is also 8. So whenever we have a constant change, whether upward or downward, you have a linear relationship. We want to find this equation that relates month with the progress percentage. So in Excel, there is something we need to go to it first. We need to right click, format trend line, or maybe you will see it, add trend line. If you press format trend line, then you will have display equation chart. This is the equation that if you enter 1 in the X, you will have 12%. This is the equation that if you enter number 2 in X, you will have Y equal to 20, all the way to 12, X equal to 12, Y equal to 100. Now, how to make sure X and Y is perfectly linear, or close to be linear, or somewhat far away from linearity? Again, add trend line or format trend line. You see this very important symbol here, R, display R squared on a value on chart. If it is 1, then you have a perfect linear relationship. If it is somewhat 0.9, 0.99, it will be tilted a little bit. But if R is 0.5, 0.4, then you will not see any line at all. Maybe lines that moving like this, for example. So this R is very important in statistics. It tells you whether or not you have a linear relationship. Now, how can I use this data, for example, to derive the equation? We have techniques we are using in engineering and science. One of the techniques here is called two-point linear interpolation. Two-point linear interpolation technique. I think technique is written like this. It basically takes 2 points, x1, y1, and takes x2 with y2. From x1, y1, x2, y2, we can develop this equation, and we can predict all of these data in a way that if I substitute here, for example, let's say x1 is equal to 3. This y will be, in this case, 28. x2 is 5. Now y will be 44. I can use these two relationships, x1, y1, x2, y2, to develop an equation, which is this one, that if I substitute 11, for example, it will find 92, even though I didn't use this point 11. But two-point interpolation technique is very useful when the data itself is linear or closely linear. Because here R squared equal to 1, then this linear interpolation will be perfect. It will exactly show 8x plus 4. What if R squared equal to 0.9, 0.8? Then if you use two-point interpolation technique, maybe you will find something like y equal to 7.7, x plus maybe 3.6, or a little bit closer than this point, 8x plus 4. Why closer? Why not perfect? Because R squared in that case will not be equal to 1. If you have R squared, for example, equal to 0.4, then you will have very bad approximation. If you use two-point interpolation technique, then it will not be working best, because it will, for example, show y equal to maybe 2x plus 2, for example. So it's far away from this real equation. So depending on the data itself, if it is linear or closer to be linear, then you will use two-point interpolation technique. We considered a perfectly linear example like this one, but let's see a close enough linear equation. It would happen if we make 36 make it 40, 44 make it 50, 52 as is, 63, 68, and 79. Now you'll see a straight line, and then a sudden jump, then a sudden drop, and so on. But it is closer enough to linearity.
So we expect the coefficient of determination, which is R, to be somewhat close to 1, right? Yeah, 0.9947, excellent to be linear, but not perfect, because there is sudden jumps here, and there is sudden drop. So that's why it's acceptable to use two-point linear interpolation, but it wouldn't produce the exact equation. So this will be the equation, right? If you put trend line, add trend line or format trend line, this plane equation on chart, it will be 7.9301 x plus 5.7. But when we used two-point linear interpolation for these 2 points, 3 and 28, maybe if we use, for example, here 2, 20, and then 3, 28, and use two-point linear interpolation, we will have this equation. We will have y equal to 8x plus 4. Is it exactly like this one? No. Is it perfectly linear, therefore? We can say no. But it is close enough to linearity because 8x, 7.9x, 4, 5.78, a little bit closer to linearity. And this deviation is explained by this very, very important term in statistics, coefficient of determination. Now, I've mentioned before, we need to see the data first to decide when we use two-point linear interpolation or another technique. Someone might say, how can we decide if we didn't see the graph? Right? Because in the exam, for example, you will not see the graph. You will be tested, and he or she will tell you that derive this equation or use whatever you want to use to derive an equation for a certain data. Then I will say, don't worry, because in this case, if you don't have the graph, then they will tell you use two-point interpolation, use another technique. They will specify it. Or they will give you the graph, and then they will let you decide. But if you are in a homework or an assignment or in some certain project in future, inshallah, you will most likely draw it yourself and then decide yourself. Like here, we decided together that this is closer to linearity, so we will not, maybe it's acceptable to use two-point linear interpolation, knowing it's not perfectly linear.
And now I will show you how to find the equation for a perfect linear example and for a closer enough linear example using two-point linear interpolation on a pen and paper. So we will take 2 points. x1 will make x1 equal to 2 because x is the month, and we'll make x2 equal to 3. y1 will be the value at x1, which will be 20, and y2 will be the value at x2, which is 28. We want to end up having an equation of this form, y equal to ax plus b. How to find a, how to find b? Well, a is the slope, and as we know, the slope is the differences of the y's divided by the differences of the x. So it will be y2 minus y1 divided by x2 minus x1. So a will equal x2 here is, or y2 minus y1 is 28 minus 20 divided by x2 minus x1, which is 3 minus 2. So the answer, if you calculate it, it will be 8. It will be 8 divided by 1, which is 8. How to find the intercept? B, in this case, y-intercept is b. You find it using one of the points. You either use x1 and y1 to find b, or you use x2 and y2, whatever suitable with you, and whatever you have a simple number. So if you have simple numbers, you will use, or you will choose this point. But if the point you are using containing commas and complicated numbers, then you want to avoid it. Here, in this case, it's a simple example. We have all of them, we have simple numbers. 2, 3, 20, 28, all are real and integers, I might say. So let's just take x1 and y1. Substitute y1 here. It will be 20 equal to a, which is 8, multiplied by x, and x in this case is 2, and then plus b. If you do calculate it, you will say b equal to 20 minus 8 multiplied by 2, which will equal to 4. The same equation that we found on Excel, if you remember, the equation was y equal to 8x plus 4. And here we found a equal to 8 and b equal to 4. So the equation that we found using two-point linear interpolation is equal to 8x plus 4. Exactly the same. So here you have a perfect linearity. The difference is always 8. So expect two-point linear interpolation to work best. For the close enough linear, again months 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. But the numbers, if you remember in the progress, were different. It was 12 here, the same, 20, 28, but here 40, then 50, then 63, 68, 79, just as the example that we showed in the Excel, 84, 92, and then 100. If we chose the same points, x1 equal to 20, x2 equal to 28, y1 equal to, no, here it should be 2, it should be 3. X's, we are taking x's here. x1 equal to 2, x2 equal to 3, y1 will be equal to 20, and y2 equal to 28. Then if you use two-point linear interpolation, you would expect to have the same equation, y equal to 8x plus 4. But because we have here differences in the middle, the difference is not always 8. Here from 12 to 28 and from 20 to 28 is 8. Here the difference is 12, 10, 13, 5, and so on. The Excel equation was different. It was y equal to, if you remember, 7.9 x plus 5.78. So here we have differences, but they are closer enough to each other. So it is acceptable to use two-point linear interpolation. It's fine. There is a third special case where the data is not perfectly linear and the data is not closer to linearity. The data is far away from linearity. Can we use two-point linear interpolation in this case? If you want your approximation to be poor and not exact and dangerous, then use it. But if you want to make sure that what you predict is true and describes the real data, then you need to understand this case. We have considered, for example, the same things that we have written over and over again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12. But the data is somewhat strange now. For the first month, we have progress percentages of 3.46 and then 2.28 or 2.82 and then 2.58, 2.44, 2.36, 0.3, 2.86, 2.26, 2.23, 2.21, 2.19, and then 2.17, 2.16. It's not organized, but we can see it. For the first month, we have this 3.46, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If we draw this data by inspection, would you expect it to be linear? When you see these very strange numbers with different pattern, with different, not fixed difference here. The difference is here about 0.7, the difference is here about 0.3. So would you expect to have a linear relationship? I want to illustrate this on Excel sheet again.
So we have this data that we've written before on the pen and paper, and we want to see what will be the graph. If you want to do that, just go to the insert button here in Excel, scatter, XY scatter, and then scatter. Then we will go to the select data, select the chart data range or the cells that we want to draw. In this case, it will be from here 1 all the way to 2.16. Then okay. So as you can see, it's not linear at all. If we draw months versus progress percentage, we will not have a linear relationship. Can we use two-point linear interpolation? It will show very, very poor approximation. It will not be near the equation that we want to find. How to show whether or not we are close or are far away from linearity? Then it's easy. We will go to display R squared, coefficient of determination, and you will see it's very far away from linearity. It's very far away from number 1. It's 0.67. So we can't use two-point linear interpolation. Maybe if the line was shown like this one, but it's not. The line is no, not this line. Wait, yeah, this one. It's different than the straight line, right? So we cannot use two-point linear interpolation because R squared is not near 0.9 or not near 1. What about the equation here? If it is not appropriate to use two-point linear interpolation because R squared is not near 1, then how can we trust this equation? We will not use it, of course. We will not use this equation to predict the data or the behavior of the progress with the months. And by the way, this equation describes this linear line, which is not related whatsoever to this line that we want to describe, the red one, the solid one. So what do we do in this case? How about if we take this data and then, for example, X, I made the reciprocal for it. In this case, it will be 1 over this cell, X, and then I repeat the process all along. The wonderful thing about Excel is that when you copy the cell here, drop it down, it will, for 12 times, because from number 1 to 12, it will show all the results we want to find. No, nothing. So here is 12. So this will be 1 over 1, this will be 1 over 2, 0.5, just the reciprocal of this. 1 over 3, 1 over 4, 1 over 5, and so on, all the way to 1 over 12. And I want to square this y. Here we have y, right? I want to square it. So I will say this value squared. How to put square? Just shift number 6 and then 2. It will be squared. Then it will be 12 here. Do exactly the same thing until I find, or until I go to the 12 point. Then we will have this data. This will be 1 over month, because I did, or I found the reciprocal, right? And here will be 1 over progress percentage. Check the wonderful thing here. If I took this data, another way to find the data, just by selecting these cells and then go to insert, XY scatter, you'll see something wonderful here. You'll see a linear relationship, right? If we draw 1 over X versus 1 over or versus, sorry, here, no, it should be progress, sorry guys, progress squared, because here we took the square of it, right? So it will be what? It will be linear. If I draw 1 over months versus progress squared, we will have a linear relationship. If I draw months versus progress percentages, we will not have linear relationship. We will not use 2-point linear interpolation here for this data, but we will use it here. So here, format trend line, display R square, you will see it's 1. So this relationship is linear.
You had this data before that wasn't linear, and now it was, or it is converted to a data that shows a linear relationship. In engineering and science, they call it fitting nonlinear data. Why fitting nonlinear data? Because I change the nonlinear data, the data that is not linear, into one that is linear. I myself, I like to call it what? Modified 2-point linear interpolation. Because indeed, we are modifying the data to do or to make it linear and then use 2-point linear interpolation. So it is kind of modified. And maybe you can also bring or have or come up with your own name, it's fine. But the important thing here is that we use it correctly. Even if you named it with your name, it has to be correct. So the equation now will not be in the form of y equal to ax plus b. It will be y squared. Y squared equal to, this is not y, wait. It will be y squared, because progress squared, equal to a, but now it will be over x, right? Because the data is 1 over x, so it has to be a over x, or a multiplied 1 over x if you like, plus b. Now we want to use this data to find a and b. So we will take, as I said before, we will take the simplest point. Here we need to take the simplest point. For example, if you take 0.5, 1 over x1 is equal, not x1, 1 over x1 is equal to 0.5, and 1 over x2, for example, is equal to, take 0.25 because it's easier, 0.25, right? It's easier. 0.5 we have 8, simple number. 0.25 we have simple number, 6. Now y2 or y1 squared will equal to the value at 1 over x1, which is 8, and y2 squared, the value at 1 over x2, which is 6. Now we want to do a simple operation. We want to find a, and a we know it's equal to differences in y over differences in x, but now it will be a little bit different. 1 y2 squared minus y1 squared divided by 1 over x2 minus 1 over x1, because the data is y squared and 1 over month. So if you calculate it, it will be 6 minus 8, sorry, divided by 0.25 minus 0.5. So the slope will be 8. And what about b? If you take one of the points, you either take 1 over x1 and y1 squared, or 1 over x2 and y2 squared. If you do so, then you will find b equal to, maybe we'll take 0.5 and 8. So it will be 8 minus 8 multiplied by 0.5. So it will be 4. b will equal to 4. So the equation y squared equal to a over x plus b will now become y squared equal to 8 over x plus 4. y versus x is not linear, but y squared versus 1 over x is linear. Then someone has to ask me, why do we need to do this? Why do we need to do changes to the data to make it linear? It seems we are going far away from the asked information, right? Because we are given the data and then we are messing up the data. We make this month 1 over month, we make this progress squared. It seems we are going far away from what is asked in the first place. But I tell you that we need to do this step and we need to find the relationship, the linear relationship, because if I use this linear relationship, it will help me predict the value for the real data in the future. So just by modifying the data and then finding a linear relationship here, I can predict what will be my progress percentages at the 18th month using this equation, the modified one. And now I will show you how. Oh, by the way, I should inform you that we already took the 7th track when we discussed the nonlinear or linearization process. Linearization means fitting nonlinear data, means modified two-point linear interpolation. All are the same. So we have this equation, fascinating equation we found, y squared equal to 8 over x plus b. No, not b, it was 4, yeah. Suppose I want to know what is the progress of my achievements, or our achievement in this case, because we are all involved in it, in the 18th month, when x1 or when x equal to 18 month. I want to know what is y, what is the progress percentages. Now, given this data, we wouldn't have known it at all, because we don't know the behavior, or we didn't understand what is happening here in the month and the progress percentages. But here we do understand the relationship here. It is linear, so we can predict what will happen in the 18th month. But under one condition here, we need to make this x 1 over x, right? Because the data that I understood has 1 over x, does not have x, so it will be 1 over 18. Make it as is, 1 over 18, because it's very complicated number if you calculate it. Look, it will be 0.100, so avoid it, make it as is. Now y squared in this case will be 8 multiplied by 1 over x, which is 1 over 18 plus 4. So the answer, I remind you that we need to understand our progress in the 18th month. Okay, so it will be, the answer will be 40 over 9. Why did I give this example? I don't know, because it's complicated. 4.444, so make it, if you put SD, it will be 40 over 9. Make it as is, 40 over 9. So, what is this 40 over 9? What does it represent? It represents the progress. Is it? Nope. Progress squared. So we need to find, if we need to find the progress percentages in the 18th month, we would have to take the square root of this one. So progress percentages, my progress in the 18th month after 1.5 years, if you want to do a conversion factor, it will be plus or minus square root of 40 over 9. I put plus or minus so that math people don't get angry with us. But because it's percentages, we should put what? Only positive here. So it will be 40 over 9. And the answer, square root of 40 over 9 is 2.1. 2.1 percentages. Which means we need to work hard because 2.1 percentages is not that high. You see, we did a conclusion here. We need to work hard, I said, because we understood the data. We found this data that was messed up, but using it, we predicted what we will be doing in the 18th month. So it's pretty fascinating, actually. The 7th drug is actually wonderful. Now, I hope you understood what do I mean by two-point linear interpolation. Why do we need two-point linear interpolation? And why do we need to understand the data? And lastly, why do we need to linearize, or why do we need to perform modified two-point linear interpolation? With all of these concepts that we've taken so far in the 7th and 6th drug, I would like to conclude with two very important models that we are using in engineering and science. I'll start with the exponential model. By the way, this is just for the sake of explanation. It's not a required thing as engineering freshman year, but it's good to know about it now. Exponential model, which has a formula of y equal to a and then exponent bx. This model describes a lot of data that are unknown to us. So we have many data here described in engineering and science that we don't know what is the relationship between one another. So we found a model that if we linearize it and then found a and b and then use it again in this equation, the a and b substituted again in this equation, it for a great chance will fit the data in the future. So how to linearize this model? How to make the equation? I didn't say it before, but a linear equation will have something like this: quantity 1 or 2, let's say quantity 2 equal to something here, quantity 1, some constant here, we call it maybe a, and then plus b. This quantity, as you remember, it was y squared, and here it was 1 over x in this example. And before, in the perfect linear example, it was y equal to x times a, or ax plus b. So we want to convert this equation into this form, so we're practically doing linearization, the same thing that we did here before. So we will say what? We will take natural logarithm. If you know natural logarithm, ln y, it's the same if I said logarithmic e with the base e and then y. And this is equal to, if you take log on the both sides, you will have ln a plus, and then ln with exponent will cancel, so we will have bx. So we made it in this form. Quantity 2, here q2 is this one, and q1 is this one, x in this case. So it will be log ey versus x will form a linear relationship. From this we will find b, which is, in this case, b is the slope here. So it will be ln y or log y, all the same. For example, for the second data, maybe minus ln y1 divided by x2. As I said before, it's just an example that provides you an insight. So the message here is we do use this linearization process in very important applications like this exponential model, or as we will see later, power law model. So it's not just something we learn for exams, we actually use it. So if you find b here, maybe for example b will be 11, my favorite number, and then you will say a, and ln a in this case, ln a will be the intercept, and then you find ln a something like 10. It's just an example, we don't know the value, but if you find it 10, then you will say a equal to exponent of 10, and then you will find a, and here you found b. So after you found a and then you find b, you substitute it again here in this equation. So you will end up having y equal to exponent of 10 and then exponent of 11x. Something like this. This equation that has this constant and that has this 11 constant will predict a lot of unknown data behavior. So it's pretty fascinating to use an exponential model because it describes many unknown data. We have another one, which is called the power law model. Again, the message here is not to understand how to find the models, it's just to show you that we really do linearization process for very important application like these models. So we have the power law model, which is of the formula y equal to a, if I recall, it is x to the power b. Yeah. Yes, yeah. A and then x to the power b. Linearize it. Linearize it means make it in the form q2 equal to q1, some constant a or some constant b, whatever, plus b. So what will happen? You will say ln in the both side. It will be ln a plus, if you take ln x to the power b, you will lower it. So it will be b ln x, something like this. So now quantity 2 is this one, and quantity 1 is ln x rather than x like in the exponential model. So we will draw ln y versus ln x, and we guarantee that this relation will be linear, r square equal to 1, coefficient determination equal to 1. After we do this, then we say b, because b is the slope, b will equal to ln y2, for example, minus ln y1 divided by, this case it will be ln x2 minus ln x1. Okay, after modifying the equation, making it in this form, then you use ln y, ln x. You don't use y and x because we modified it. So if then you will find b in this case. What about a? A will be something like, in this case, yeah, it will be exponent, as we found before, exponent to the power number, in which we know this number, by the way, right? Because ln a equal to number, certain number, we will find it using using b and then using two data or one of the datas. And then if you find a, some number here, you will say a equal to exponent of that number. So after you find a, you find b, you resubstitute it again here in the above equation, and then you have something of the form y equal to, let's make this number maybe 6, 6, and then it will be exponent of 6. Here b will be 7 maybe, so it will be 6 x to the power 7. And we're claiming that this equation will describe many of the unknown data that we face in engineering. So that's why we are introducing the concept of power law model and exponential model. It's not part of the video. If you skip it, it will not affect anything about you or about your learning, but it's good to gain this information earlier now. And if you have any question, of course you can ask me. I will answer any question. So I guess this is the end of the video. Today we will take only 2 drugs, nothing more than this, because they're quite intensive, especially the 7th drug. So I believe that's all I have, and then maybe the next video I will make exercises about this chapter that talks about significant figures, dimensions, conversion, graphing, like this one, like this video, and also dimensional analysis.